Welcome back to Bite-Sized Breakthroughs, where we break down complex research into digestible bites. Today we're diving into a fascinating paper titled Rethinking the Role of Scale for In-Context Learning, an interpretability-based case study at 66 billion scale. Joining us is Dr. Paige Turner, the lead researcher on this project, and Professor Wide Spectrum, a leading expert in the field of large language models. Welcome, both of you.
Thank you for having us, Alex. It's great to be here.
Paige, let's start with the basics. What's the central question this research addresses?
Sure. This paper delves into the role of scale in in-context learning for large language models. Specifically, we wanted to know if all the components of a massive LLM are truly necessary for it to perform in-context learning well.
That's a really interesting question, Paige. Why is that important?
Well, Alex, the field is obsessed with bigger models. Everyone assumes that a larger model is always better. But we wanted to see if that's actually true, especially in the context of in-context learning. If we can show that a lot of the model is unnecessary, it could lead to more efficient and resource-friendly language models.
Professor Spectrum, you've been working with LLMs for a long time. Can you give us some historical context for this question?
Absolutely, Alex. The field of natural language processing, NLP, has been revolutionized by the rise of large language models, particularly those based on the transformer architecture. These models, trained on massive datasets, have shown remarkable abilities in performing tasks without fine-tuning through the in-context learning paradigm.
So in-context learning is kind of like teaching a model by example, right?
Exactly, Alex. You provide the model with a few or zero examples of input-output pairs for a particular task, and the model learns to generalize to new inputs. This ability for few-shot learning is quite fascinating.
So Paige, how did you actually approach this question? What methodology did you use?
We used a combination of two main approaches. First, we focused on task-specific importance scores and structured pruning. We analyzed the contribution of individual components, attention heads, and feed-forward networks to the model's ability to perform in-context learning. We then iteratively pruned these components and observed the impact on performance.
Can you explain what those components are, Paige? Especially for listeners who aren't familiar with the transformer architecture.
Of course. The transformer architecture is built on a stack of layers. Each layer has two key components: attention heads and feed-forward networks. Attention heads are responsible for identifying the relationships between different parts of the input sequence, like words or phrases. The feed-forward networks then process this information to generate a representation of the input that can be used for making predictions.
So you're saying that you basically cut out parts of the model and see if it still works well.
That's right, Alex. We used two methods to determine the importance of these components: Oracle importance scores and gradient-based importance scores. The Oracle method involves removing a component and measuring the drop in performance. Gradient-based scores, on the other hand, use the gradient of the loss function to estimate the sensitivity of the model to changes in that component.
That's very comprehensive. But what about the task-agnostic approach? What did that involve?
In this approach, we looked at the capacity of individual attention heads to perform primitive operations related to in-context learning. These operations are things like prefix matching and copying, which are more basic building blocks of how the model might process information.
Could you explain those primitive operations a little more, Paige?
Certainly. Prefix matching refers to the model's ability to identify a prior occurrence of a token within the context. For example, if the model is learning a language translation task, it might use prefix matching to recall previously translated tokens. Copying refers to the model's ability to directly copy information from the context, like copying the suffix of a previously encountered token.
So you're essentially looking at the basic mechanisms of how the model learns from examples.
Exactly. We wanted to see if the attention heads that are good at performing these primitive operations are also the ones that are important for performing more complex tasks. And indeed, we found that there's a lot of overlap.
Professor Spectrum, is this approach of analyzing primitive operations a new concept?
It builds upon the work of Olson et al., 2022, who introduced the concept of induction heads, attention heads that are particularly good at performing these primitive operations. This paper expands on that by showing that these induction heads are not just important for basic tasks, but also play a role in more complex downstream tasks.
So, Paige, what kind of model did you use for this experiment, and what were your key findings?
We used the Open Pre-trained Transformer OPT model, specifically the 66 billion parameter version, OPT 66B. It was the largest publicly available decoder-only language model at the time of our experiment. Our key findings were quite surprising.
And what were those findings, Paige?
We found that we could remove up to 70% of the attention heads and 20% of the feed-forward networks in OPT 66B, with minimal decline in performance across a diverse set of 14 NLP tasks. That's a huge amount of redundancy. This suggests that these models might be over-parameterized for in-context learning. We could potentially achieve similar performance with a much smaller, more efficient model.
Wow, that's a significant finding. Do you have any specific examples of how this pruning impacted performance?
Sure. For example, when we removed 70% of the attention heads in the zero-shot setting, we only saw a 5% drop in average accuracy across all tasks. This is really significant considering the massive scale of the model. And the results were similar in the few-shot settings, where we saw a 6% drop in accuracy with 70% of attention heads pruned in the one-shot setting and a 4% drop in the five-shot setting.
Professor Spectrum, how do these findings fit into the broader context of language model development?
Alex, this research offers crucial insights into the current state of language modeling. It challenges the prevailing assumption that bigger is always better. We see that a core nucleus of components, rather than the sheer size, might be driving the in-context learning capabilities.
Paige, did you find any patterns in terms of which components were more important for in-context learning?
Yes, we did. We found that the important attention heads were primarily clustered in the intermediate layers of the model. This suggests that these layers play a crucial role in integrating information from different parts of the sequence. The feed-forward networks, on the other hand, were more important in the later layers, especially for tasks with longer sequence lengths.
So you're saying that there's some kind of division of labor within the model?
That's a good way to put it, Alex. It seems that different layers are responsible for different aspects of the processing. And while the induction heads, those that are good at basic operations, are spread throughout the model, they are particularly prevalent in the upper layers. This suggests that they contribute to the more abstract, conceptual aspects of in-context learning.
Professor Spectrum, can you elaborate on the implications of these findings for the future of language models?
This research opens up exciting avenues for the field. We now have evidence that smaller, more efficient models can achieve comparable performance in in-context learning. This could lead to more resource-friendly models that are more accessible to a wider range of users and applications. Furthermore, understanding the role of induction heads could allow us to design training methods that specifically enhance these heads, potentially leading to more robust and effective in-context learning abilities.
That's fantastic. But Paige, were there any limitations to your study, any areas where you see room for future research?
Absolutely, Alex. Our pruning approach was a greedy one, where we removed components one at a time. This method might not be optimal, and we could potentially achieve better results with more sophisticated pruning strategies. We also only looked at two primitive operations related to in-context learning. It would be interesting to explore other potential operations and their relationship to task-specific important heads.
That makes sense, Paige. What other directions could this research go in?
We could explore pre-training objectives that are specifically designed to enhance the formation of induction heads during training. It would also be interesting to replicate this study using instruction-tuned models, which have become increasingly popular. And of course, we need to conduct more in-depth analysis of the relationship between in-context learning performance and the diversity of in-context examples.
Professor Spectrum, what are your thoughts on the potential impact of this research?
This research has the potential to revolutionize the field of language modeling. It challenges current assumptions about scale and offers a more nuanced understanding of in-context learning. The focus on induction heads and efficient model design could lead to significant advancements in how we build and utilize LLMs.
Paige, how do you see these findings impacting the applications of LLMs?
It could lead to the development of more efficient and accessible LLMs for a wide range of applications, such as more resource friendly models for use in resource constrained environments, LLMs tailored to specific tasks by focusing on relevant induction heads, and improved performance of existing LLMs through structured pruning.
That's really exciting. So, Paige and Professor Spectrum, can you summarize the main takeaways from this research?
In essence, this paper shows that a significant portion of the components in massive LLMs might be redundant for in context learning. It also identifies a small set of attention heads, called induction heads, that are critical for this learning process. These findings suggest that we can potentially achieve similar performance with more efficient models, and that by focusing on enhancing these crucial components, we can improve the effectiveness of in context learning in LLMs.
Thank you both for sharing this groundbreaking research with us. It's fascinating to see how we can optimize these powerful tools and better understand how they learn.